Hello, everyone, and welcome to part 2 of the Chapter 9 notes, where we're going to be talking about moment of inertia. And I refer you to page 12 in your notes packet when you're taking a look at this thing. Now, you may have noticed, if you've ever, twiddled with a pencil absent-mindedly, that it's a lot easier to twiddle the pencil if you're holding it about its center of mass, as opposed to trying to twiddle it if you're holding it by its very edge. And there's a reason for that, as we're going to explore in this particular chapter or in this particular section. The idea of a moment of inertia is essentially how much resistance you have to a change in velocity, in this particular case, a change in angular velocity, is going to be dependent on an object's shape as well as how you are rotating it. So, for instance, the moment of inertia of a loop where you're rotating this about the central axis is going to be greater than if you actually have a solid cylinder or disk which you're rotating about the center of the disk. And it's easier to rotate a solid cylinder about its central diameter as opposed to, and we're going to see later, if you're going to be rotating it by the very end. And it's even harder still if this thing that you're rotating by its end has a ball or something which is stuck to the end of it, as you might well imagine. Unfortunately for a virtual course, there are a lot of very good demos that really don't have the same impact if you're seeing them online. However, I will find some links on YouTube to some relevant demos of moment of inertia and post them in the comments, or rather in the information of this particular video. All right, and one of those is the blue and red wand demo. Again, this would make a lot more sense if we were actually in the classroom, but again, I'll try to find some kind of a video. So the kinetic energy of rotation. To find the rotational kinetic energy, you want to treat a rotating body as a collection of particles with different speeds and add up the kinetic energies of all the particles to find the total energy of the body. So if you're looking for the kinetic energy of the entire body, that's simply the kinetic energy of one particle and plus a second particle, plus a third particle, up to however many particles you actually have. Now, remember that the velocity, the linear velocity of a particle, is equal to omega r. So if we substitute this in for the above, what we have is the kinetic energy is equal to the sum of 1/2 m times omega I Ri squared, or if you just distribute that squared term, you get this expression, sum of mi/ri squared, omega squared. And this is, again, assuming that omega is the same for all particles, which most of the time is a fairly fair assumption when you're dealing with some sort of solid mass. After all, when I'm rotating this particular pencil or something like that, remember that the angular velocity is the same for all of the particles in that pencil. It's only the linear velocity that's going to be different. So the quantity in parentheses on the right side is called the rotational inertia, or the moment of inertia. I of the body and this is denoted with the letter I, which is with respect to the axis of rotation. It's a constant for a particular rigid body and a particular rotation axis, and you have to specify the rotation axis. As we're going to see, the rotation axis that will give you the lowest moment of inertia is a rotational axis which is drawn through the center of mass. And other rotational axes will have a higher moment of inertia. But you have to specify where you're rotating this particular body from. And you can see, I hope, how the shape is going to matter. If you have something that is relatively compact, and relatively circular, and you're rotating about that center, that's going to be very different than if you have a long rod where you have a very long radius and you're rotating it by the center, which in turn is going to be different from the case where you have a rod and you're rotating it by the end. So the radius that you're looking at can become very long indeed. It's the entire length of the rod. So again, you can kind of see where this is going, or I hope you can see where this is going. We're going to elaborate this in the next few slides, and that the moment of inertia, I, for particles, is equal to the sum of mi/ri squared. And that is what the moment of inertia is defined as. The SI unit of the moment of inertia is kilograms times meters squared, and the rotational kinetic energy is supplied by the expression K equals 1/2 I omega squared. And you'll notice that this looks an awful lot like the kinetic energy expression that we all know and love for linear motion, but in its place, we have replaced the moment of inertia for the mass. So this is kind of serving as an analog of mass. You can kind of see the moment of inertia as being a resistance to rotation, if you will, or resistance to rotation through a particular axis for a particular shape. So that's kind of, again, an intuitive way of understanding it. All right, to reduce the moment of inertia, what you want to do is have your mass as close to the axis as possible. So it's easier to start the apparatus rotating if you have a large mass close to the rotation axis, as opposed to where you have two masses which are way on the side of this rotation axis. And again, this can be sort of derived from our formula, where, let's see if I can back up one slide. Because this is a sum of a mass times the radius squared, if you have a mass at a very large radius, that's proportionally going to add more to your moment of inertia than if you have the same mass at a very short radius. So again, remember that moment of inertia is not only mass dependent, but radius dependent. So the smaller moment of inertia is if you have a large mass which is close to where you're rotating, and you have a higher moment of inertia with the same mass if those masses are located further away from your rotation axis. And again, I refer you to a demonstration of this, which I'm going to find and post in the description of this particular video. All right, since the moment of inertia of an ordinary object involves a continuous distribution of mass at a continually varying distance from any rotation axis, the calculation of moments of inertia generally involve, you guessed it, calculus, where we're looking at very small changes in continuous variables and adding all of those small changes together to give us a complete picture. Now, fortunately for us, a lot of these moments of inertia have already been calculated for a lot of common shapes. And for the most part, I'm going to be providing you with what those moments of inertia actually are. That's not to say that I won't ever ask you to calculate a moment of inertia, but just realize that a lot of this information is already out there. If a rigid body consists of a great many adjacent particles and it's continuous like a frisbee, you can consider an integral and define the rotational inertia of the body as I is equal to the integral of r squared dm, where m is a very small little segment of mass. So what we have is, let's say that we have some arbitrary shape like this, and we're just considering the mass of this tiny little slice here. That's what we're going to refer to as dm. And of course, as you might imagine, what we're doing when we're calculating this integral is moving dm very slowly down this particular rod and adding up all little slices of dm, taking into account the distance of dm from some axis, which is going to be r squared in this particular case. All right. So as I've said, a lot of these have already been calculated. So let's have a look here. A slender rod with the axis through the center has a moment of inertia of 1/12 times the mass times the length of the rod squared. Whereas if you have the axis through one end of that same slender rod, the moment of inertia is equal to 1/3 ml squared. And you'll notice that this moment of inertia is going to be 4 times larger than this moment of inertia, again, assuming that the rod has the same mass and it is the same length. In a rectangular plate with an axis through the center, The rotation about this axis is going to equal 1 over 12 m times a squared plus b squared. And if you're going to instead rotate along an edge, so in other words, if you take this plate and you kind of flip it over like that, I'm sorry, that sort of blocks your view. If you rotate it like this, then the moment of inertia is 1/3 ma squared, where a is this length right here. If you're looking at a hollow cylinder, the moment of inertia is 1/2 m times r1 squared plus r2 squared, where r1 is the radius to the inside of that cylinder, or sort of the inner edge, if you will, of this mass, and then r2 squared, r2 being the sort of to the edge of the donut, if you will. So R1 being the distance to the inside of the donut, R2 being the distance from the center to the outside of the donut. Solid cylinder, I equals 1/2 mr squared, and a thin-walled hollow cylinder, I equals mr squared, and so on and so forth. And again, it depends on the composition of the, it depends on the shape, it depends on the composition, it depends on where you are rotating this thing, what your moment of inertia is going to be. But again, there are handy tables, and a lot of this has been calculated already. Okay, so let's take an example of this and see what we can do with our moment of inertia. So some European trucks run on energy stored in a rotating flywheel with an electric motor getting the flywheel up to its top speed of 200 pi radians per second. One such flywheel is a solid uniform cylinder with a mass of 500 grams and a radius of 1.0 meters. It's asking us first what the kinetic energy of the flywheel is after charging, and second, if the truck uses an average power of 8.0 kilowatts, for how many minutes can it operate between chargings. So the basic idea here is that energy is being stored in a wheel. So we have a wheel that we've sped up. This wheel is turning, and it's gradually giving its energy back up to the rest of the system, or to what it's plugged into. So the flywheel is storing energy in the form of kinetic energy, in the form of motion, which can then be used to run other systems in the truck. So let's go ahead and take a look at how to solve this problem. The moment of inertia from table 9.2 is I equals 1/2 mr squared. Don't just take my word for it. We're looking at a solid cylinder. So we are looking at this particular case. And I, in this case, is equal to 1/2 mr squared. Okay? So we know that. And we know that the rotational kinetic energy is given by K equals 1/2 I omega squared. And so all we have to do is substitute. This first 1/2, so this 1/2 here is analogous to this 1/2 on the outside of the parentheses. The 1/2 on the inside of the parentheses is this. So this is I, and the substitution's right here. So we have 1/2 times the mass, which we're given as 500 kilograms, times the radius of 1.0 meters squared. We then multiply that by omega squared. So this here, this whole part is I. This part here is omega squared. We know that the initial speed is 200 pi radians per second. We square that. We go ahead and we have this entire expression that we've plugged into. We solve it, and we find that our answer is 4.9 times 10 to the 7th joules. All right. So how about that power question? If the truck uses an average power of 8.0 kilowatts, for how many minutes can it operate between chargings? Well, we know that 1 watt is equal to 1 joule per second. So 8,000 watts is equal to 4.9 times 10 to the 7th joules over what time? Again, this is the amount of work that can be done by the energy that is stored in that rotating flywheel and that rotating cylinder. We know that you have to produce the power of 8,000 watts or 8.0 kilowatts over some period of time. We simply solve for t, and we find that t is equal to 6,125 seconds or 102 minutes. So just another kind of simple example of how you can use this to solve problems. And what I'd like you to think about is, okay, if you're going to design some kind of flywheel and you want to store kinetic energy, what would be the best shape that you would want to use in a case like this? Well, you would ideally want something that has a high moment of inertia. And again, ideally, that would be something like a thin-walled hollow cylinder or a solid cylinder, as opposed to rotating a slender rod through the center, because the moment of inertia is much less. Why were we using a solid cylinder as opposed to a thin-walled hollow cylinder? Well, it has to do with the other factor in our calculation of kinetic energy, and that is mass. As you might imagine, if you have a solid cylinder, that solid cylinder is is solid and is therefore going to have a higher mass than a thin-walled hollow cylinder made out of exactly the same material. Okay, so just a little engineering consideration and an application of this idea to the real world. All right, in the second problem, we have 4 particles at the corners of a square connected by massless rods as shown. And the question is, what is the moment of inertia about the system in the y-axis? So we're saying that the axis of rotation is outlined here in red. It's this y-axis, and we're going to give it a twist in this direction. So essentially, we've got our square, and we're sort of flipping the square this way. I'm trying as best I can to keep my thumb and everything in a locked position, and we're rotating about that way. All right, so if we're trying to find the moment of inertia, what we have to say is the moment of inertia is equal to the sum mi/ri squared. And what does that mean in a practical sense? Well, the radius from the axis here to this point is 2 meters. We're shown that that's what we're shown here. And because this is a square, that's also, again, 2 meters. So when we go ahead and calculate what the moment of inertia is going to be, and we start from this point up here when we're doing our summation, what we have is 3 kilograms times 0 meters, because it's on the rotational axis, plus 4 kilograms times 2 meters squared. This distance is 2 meters, and we're adding this into the sum of our masses, or into the sum that we're taking here to find the moment of inertia. So 4 times 2 meters squared plus 3 kilograms times, once again, 2 meters squared. So that's where that is coming from. And finally, 4 kilograms, this last point here, it's on the axis of rotation, and therefore it is 0 meters. And we go ahead and we do this sum, and we find that the total is 28 kilograms per times meters squared, which is our moment of inertia. All right? So that's good. I mean, we found a way to calculate our moment of inertia, and we know that a lot of moments of inertia have already been calculated for us, and we have handy tables. But the problem is there are infinitely many possible axes through which you can rotate something. I mean, again, if I've got this pencil, I can rotate it about this axis. I can rotate it just slightly over here about that axis. I can rotate it by its end. I can rotate it by its other end. I can rotate it this way. I guess if you insist, you can rotate it that way. There are all sorts of ways that you can, an infinite possibility of ways that you can rotate this particular pencil. So how do you go about finding the moment of inertia for these other axes? How do you relate information that you already know, which is already given, to something that you would like to find out. And this is where we make use of something called the parallel axis theorem. And the parallel axis theorem states very simply that if h is a perpendicular distance between a given axis and the axis through the center of mass, these two axes being parallel, then the rotational inertia I about the given axis is given as I equals I of the center of mass plus m times h squared, where I is the moment of inertia through some point P, I center of mass is the moment of inertia at center of mass, m is the total mass of the body, and h is the distance between the parallel axes. All right, so let's take an example, and unfortunately this didn't really pop up very well, but let's say that the center of mass in this first example, in this kind of weird shape here, is O. So that is going to be the center of mass. All right, and let's say that we want to think about an axis that's perpendicular to that center of mass about which we're rotating it. And let's say that that axis is going into and out of the page. So think of the axis being in and out, and we're going to rotate this entire kind of weird square-like shape this way or this way. All right. And let's say that we're interested in comparing it to some point of rotation P here, which is some distance away from the center of mass. And let's say that the x and y coordinates of P are A, so the distance between the center of mass and P in the x direction is A, and we say that the distance between the center of mass and P in the y coordinate is B. And then we say, all right, we're going to let dm be a mass element with the general coordinates of x and y. So again, that's that little segment, that little fragment that we're going to be taking when we're summing up our moment of inertia. So the moment of inertia is equal to the integral of r squared dm, which is equal to the integral of the magnitude of x minus a plus y minus b, or sorry, is equal to the integral of the absolute value or magnitude of x minus a squared plus y minus b squared dm. And again, this is just what the radius is going to be if we're, again, considering this point P here. All right. So if we're considering distance from this point P, because that's the axis of rotation we're actually interested in, you wind up with this sort of thing popping up. So if we go ahead and rearrange and do some simplifications, we wind up with the following integral. So we have integral of x squared plus y squared dm minus 2a integral of x dm minus 2b integral of y dm plus integral of a squared plus b squared dm. But this guy right here, x squared plus y squared, this is just the distance to the center of mass. Okay? And so what we can say is that this first integral here is simply I of the center of mass. All right? And then this last term here, this guy right here, is simply mh squared, where m is the body's total mass. All right? And if we put this all together, eventually we'll put this all together, you end up with the simplification of this particular set of integrals back to this central axis theorem. All right. So what's really exciting about this simplification is if I want to determine the moment of inertia through some axis, I don't necessarily have to sum up every single little point of mass. All I have to do is compare it with something that's presumably already known, which is the moment of inertia through the center of mass, and factor in the distance of that parallel axis from the center of mass. So again, if I've got again, this pencil is doing very good duty today. If I know what the moment of inertia is, if I'm rotating it by its center of mass, this might not be exactly the center of mass, but it's close enough for video work. All I have to know, if I want to say, okay, what's the rotation through this axis? What's the moment of inertia for rotation of this axis? What I have to know is the mass of the pencil and the distance between this axis here and this axis here. Again, presuming that these axes are parallel. And by the same token, if I was going to rotate, this way, so if I'm rotating this way, as opposed to rotating that way, again, same story applies, but you have to know the difference between the parallel axes. If you know the moment of inertia through the center of mass, which again is usually something you can look up in a table, and you know the distance to the parallel axis and you know the overall mass, you can very simply find the moment of inertia through some other axis for some other rotation. So it's a very powerful and very handy tool, a very handy theorem to make your life a lot easier and a bit less calculus full. All right, so I put this back up here again because in a little bit we're going to be taking a look at something that requires this particular table. All right, so you already have these shapes here in mind. So the next problem is asking us to calculate the rotational inertia of a meter stick with a mass of 0.56 kilograms about an axis perpendicular to the stick and located at the 20 centimeter mark. So again, we've got a meter stick. We know what the rotation is going to be about the center of that meter stick. We're trying to find the moment of inertia about some other point that's off of the center of that meter stick. So we use the parallel axis theorem, I equals I center of mass plus mh squared, where I center of mass is the rotational inertia about the center of mass, which is equal to I equals 1 over 12 ml squared. So we're using, in this case, this moment of inertia. It's the moment of inertia for the rotation of a slender rod with an axis through the center. And we're saying that this slender rod is what our meter stick is, and we're rotating about the center. All right, and that's equal to I equals 1 over 12 ml squared, where m is the mass and h is the distance between the center of mass and the chosen rotation axis. So the center of mass is, as you might imagine, at the center of the meter stick, which is at the 50 centimeter mark because it's a meter long. That's why it's called a meter stick. So the center of mass is at the 50 centimeter mark. We're asking about what happens if we rotate about the 20 centimeter mark. So the distance between the 50 centimeter mark and the 20 centimeter mark is going to be 30 centimeters. So what we find, again, applying the parallel axis theorem, is that I is equal to 1 over 12 times the mass of the meter stick and the length of the meter stick. This is the total length of the meter stick that we're using. So this is the ICOM component. And then to which we are adding mh squared. And that's what this component is here. All right. So again, we know that the length of the meter stick is 1 meter. It wouldn't be much of a meter stick if it wasn't. And then the total mass, again, this is the total mass of the meter stick times h, the distance of this rotational axis that we're interested in from the center of mass, squared. And so we go ahead and we find these values. and we conclude that the moment of inertia of this particular meter stick in this particular rotation is going to be 0.097 kilograms times meters squared. Okay, so a straightforward example of the parallel axis theorem in action. Now that we've taken a simple look at the parallel axis theorem in action, let's take a more complicated look at the parallel axis theorem in action with a more complicated problem. So let's say that we have a rod of length 2.26 meters, and the mass of the rod is 3 kilograms, and it's connected to a sphere of radius 1.23 meters and a mass of 5 kilograms as shown in the figure below. So essentially we've got a stick and we've got a ball on the end of that stick. And we're asked to find the system's moment of inertia. For this type of problem, we can actually break it into 3 parts. If we're looking for the total moment of inertia, I total, about this axis, so about this particular point, we can say that that is simply the sum of the moment of inertia of the rod about an end, the moment of inertia of a sphere about its center, so here, and then a parallel axis contribution. What does that mean with a parallel axis contribution? Well, we're saying that this axis here, rotating the sphere about its center, and this axis here, rotating this rod-ball combination, these axes are parallel to each other, and what we want to find is basically the difference between the rotation around these two axes. So these are the two parallel axes that's going to determine our parallel axis contribution. So to do all of this, first thing we want to do is take a look at what I rod about end and I sphere are. And we'd seen on the previous slide that a slender rod with the axis through one end has a moment of inertia of 1/3 ml squared, and the moment of inertia of a solid sphere is I equals 2/5 mr squared. Okay? So we go ahead and substitute these values. And what we're doing here is noticing that this is the moment of inertia of the rod. This is the moment of inertia of the sphere. And we're substituting in or plugging in the expressions as appropriate. Note that for the moment of inertia of the rod, we're using the mass of the rod and the length of the rod. For the moment of inertia of the sphere, we're only using the mass of the sphere and the radius of the sphere. And then we have that parallel axis contribution. In this case, the parallel axis contribution is the mass of the sphere times L plus R squared. And why would that be? Well, we have one axis here, that's the axis we're interested in, and we have the parallel axis going through the sphere. We're interested in measuring the effect of the parallel axis on just the mass of this particular sphere because the rod is already accounted for in this first moment of inertia. So in the rod about end, all of the moment of inertia contribution of this rod is already taken care of. But we're interested in the contribution of the sphere to the overall moment of inertia. We know the moment of inertia of that sphere, and now we're just looking at the contribution made to a parallel axis. So we're just using the mass of the sphere. In this case, we don't care about the mass of the rod. And the length, or the distance, the h that we're using, is going to be the radius of the sphere, r, plus the length of the rod, L. The total distance from this sphere's center of mass to the place where we're rotating the rod is going to be r plus L. So this whole distance here, which is why we have m sphere, L plus r squared. We go ahead and we make our substitution. So I equals 1/3 m rod L squared plus 2/5 m sphere r squared plus m sphere L times r. And I thought I had fixed this squared. And we go ahead and we plug in all of the values that we're given. okay? And when we evaluate, one thing that you'll notice is, well, first you'll notice the answer, which is 69.04 kilograms times meters squared. But note the relative contributions of each of these things. It's the moment of inertia of the rod about its end, and then the moment of inertia of the sphere. But the largest single component of this entire calculation is that parallel axis component. So this is, again, a rather dramatic example of what a big difference it makes to rotate something about a parallel axis rather than rotating something about its center of mass. And this ball here is making a big contribution to how difficult it is to actually spin this rod-ball contribution around. And that is going to be made much worse the longer you make the rod, or the bigger you make the sphere, or the more massive you make the sphere. All right. So I hope that served as a good introduction to the idea of a moment of inertia, and I hope that you tune in next week for Chapter 10, which is Dynamics of Rotational Motion, wherein you're going to learn exactly why it's a good idea to turn a wrench by its end as opposed to turning a wrench by its part that's very close to the nut that you're trying to loosen. In the meantime, I've posted a list of 4 other YouTube videos. 2 of them are demos. One of them is a combination demo and explanation. Sorry, scratch that. Of the 4 videos, all 4 of them have demonstration components, and one of them has a bit more of a lecture-based component. The first 2 videos are the red/blue wand demonstrations that are mentioned in the lecture notes, so I urge you to see exactly what they're talking about. It's a really cool and very clear demonstration. There's another demonstration of the idea of moment of inertia, along with a bit of a lecture component. That's going to be in the flipping physics video, which has a link in the description of this video. And finally, my friend Zach Tobin is going to demonstrate how exactly changing a moment of inertia changes somebody's rotational velocities. And this is basically someone standing on a stool, holding a couple of barbells, and greatly speeding up when those barbells are brought closer to the person's center of mass. All 4 of them are well worth it, and all 4 have links in the description of this video. Thank you very much, and I will see you next time.